before, like how do we know which of these tests to apply? How do we know when it's a one sample t-test, a two sample, equal variance, unequal variances? But that's exactly what we're going to try right now. Okay, we're going to try these. Some of these we're going to try just with SPSS, but a lot of them we're going to try both ways, doing it by hand and doing it by SPSS. There are some that are not going to, SPS is not that friendly towards like proportions, for instance. Okay, so the first thing we have to recognize is that all of these tests, when we're working with a t-test, we're always working with a numerical variable, right? So we're always comparing, say, blood pressure, blood sugar, weight, height, or something like that, but we're comparing it using two groups that are in a categorical, that are defined by a categorical variable, like gender, male or female, or placebo and drug, and so on and so forth. So there's always two variables involved. One of them is always a numerical variable, and the other one's always a categorical variable. So up to this point, the t-test, the categorical variable is only going to have two values. Only going to have male or female, only going to have placebo drug group, placebo group or drug group. It's only going to have smokers, non-smokers, and so on. Later on, now of course, let's say you wanted to compare a numerical variable like blood pressure by ethnicity. You have more than two ethnicities. So the t-test may not work that well unless you're going to limit yourself to two ethnicities, comparing two ethnicities rather than say 6 or 7 or 8 or something like that. We're going to learn another test later on called analysis of variance. That's going to be like the t-test, but it's going to be applied to situations where the categorical variable that we're working with has more than two values. But for right now, we're looking at a numerical variable and a categorical variable. Okay, so there's going to be certain situations that we're going to be in for starters. Number one, sometimes we're going to be comparing a sample that we take to a known mean, right? And since there's only one sample, one group will know the mean of the population. The other group, we don't know the mean of the population, so we have to get it through us. We have to estimate it through a sample. And we want to see if the two populations have the same mean. That's not going to happen that often, right? Because we're very rarely going to have a situation where we know either one of the means. Much more often, you're going to see situations where you're taking two samples from group A, samples from group B, and comparing the two of them. Now, on occasion, you're going to have a situation where somebody's done a study previously that sampled a very large, that was a very large sample of a particular population, and you feel that it's a big enough sample that you have a pretty good handle on what the true mean is for that population. So in that case, you may say, okay, let's call that a population mean, and now let's go take our sample of this other group. Okay, so occasionally we're going to have a single sample, but you're going to recognize that immediately because there's only one group that's actually sampled. That's the sample size. So the minute you say two sample sizes, you know you're working with two samples, right? So if you only one sample size, work with one. Most of the time, we're going to be working with two samples. Now, two samples means we're going to sample this group, we're going to sample this group. Sometimes the sample sizes are going to be the same. Sometimes they're going to be different. Okay, a lot of times you start out with equal sample sizes, and then somebody has to drop out, or you find there's an outlier or something like that, and you wind up they're not exactly equal. The other thing we're a little concerned about the sample size of the two groups, but we're also concerned about the variance. When we have equal variances, or the variances are so similar that we think that there's good reason to believe they're equal, we can gain a big advantage by combining those numbers from the two groups so that we have a single combined variance. In other words, if I say I want to compare the blood pressure of smokers to non-smokers, I may say to myself, well, maybe smokers have a higher average blood pressure than non-smokers do, but I don't have any reason to believe that the variability is different. In other words, that the spread is different. Maybe just the mean is different. So in a case like that, I want to combine the two of them. So instead of basing my standard deviation, my estimate of the population standard deviations on a sample of, say, size 50, if there's two groups of 50 each, now I can base it on a sample of size 100 and get something more equal. On the other hand, we may have situations when we do a sample and we calculate standard deviations, we can see they're quite different. Group A, the standard deviation is 10. Group B, the standard deviation is 20. So we can have two samples that we take. We can have it with equal variances, or we can have it with unequal variances. Okay, we're going to see that when we work with SPSS. We'll see two rows. SPSS actually calculates all the t-scores both ways. Equal variances assumed or unequal variances assumed. The last thing we have is proportions, where we're going to compare the proportion of one group to the proportion of other group. In that case, we're dealing with two categorical variables. See how it doesn't really fit quite as well with the t-score? Because I was talking about numerical variables and categorical. Now we have two categorical variables. Diabetes, no diabetes, smoker, non-smoker, right? Each one of those is a categorical variable. We express it as a percentage or proportion. 10% of smokers have diabetes, 4% of non-smokers have diabetes, and so on, right? So we're dealing with a proportion. We look at the proportion as a point estimate. It's just the way we would work with a mean, but we know that it's not really a mean. It's a kind of a different kind of process. In fact, is that really governed, the distribution of proportion, is that really governed by the normal distribution? Anybody remember what kind of distribution that was? Right, there's two choices, diabetes, not diabetes. What is that distribution called? Binomial distribution, right? It's not really a normal distribution. A lot of the time it will mimic a normal distribution, it'll be similar to, but it's not the same as a normal distribution. Analyses that work with normal distributions are called parametric. Analyses that work with distributions that we don't assume to be normal are called non-parametric. When we look at SPSS, we're going to see that there's an area in there where we can get to certain analyses that are called non-parametric. We're going to stay away from that for this class. I'll just show you where they are, so if it comes up in the future, you know where to find it. But for this, you'll see that there is a way to do these, analyze these proportions using that area where you have non-parametric statistics. But for the most part, we're going to work with that manually rather than using SPSS. Manually, I mean using Excel or a tool like that. Okay, so now the other thing that we want to keep in mind is some of the time we'll know the population standard deviation, but most of the time we won't know it, so we have to estimate what the population standard deviation sigma is based on the sample standard deviation S. Okay, so we're going to keep that in the back of our heads. And we're also going to be worried about whether our analysis is single-sided or two-sided. I'm almost always going to talk about two-sided analyses because they're more conservative. You're going to do them almost all of the time. You're going to relatively rarely take advantage of single-sided. Single-sided, what you're doing is you're assuming that your result can only be in one direction. In other words, if you're analyzing male and female heights, you're assuming if you sample two populations, male and female, from two different populations, you're assuming that the female population can only have an average height that's shorter than the male population. Sometimes that makes sense. Most of the time, you rather than take advantage of the fact that it's easier to prove that because it's single-sided, most of the time you're going to analyze it two-sided anyway to make it a more conservative analysis. A little tougher to prove. Maybe you have to have a little bit bigger sample size, but it's probably a better way to approach this stuff anyway. Okay, so these are the things that we're going to be concerned about right here when we choose what tests we're going to use. So we have a document. We have a document that has some exercises that you can download from Blackboard. I'll go over them now, and I also have a data set, Excel data set, and an SPSS data set for each of the exercises that are in that document. Okay, so I just want to get to the next thing here. Okay. So now I just talked about all the different kinds of tests that you can be doing. So now here is the formulas that you're going to likely be using depending on what kind of tests that you're going to be doing. So for instance, in one case, you might be doing comparing the means of two populations, right? Well, what do you do if the standard deviations are assumed to be equal? If they calculate standard deviations from the two samples, they look equal. Well, how do you deal with that? Well, the way that you deal with that is that you need to calculate a standard error in order to calculate your z-score, right, to calculate your p-value and so on. And the way we're going to do that is we're going to take advantage of the various formulas that are built in here for that particular situation. So here is the formula that we would use for the standard deviation of a, if we assume equal variances. If we're assuming equal variances, we're going to pool the standard deviations for the two groups. And we're going to use, for the pooled standard deviation, we're going to use the sample size minus 1 times the standard deviation of the first group squared, plus sample size number 2 minus 1 times the standard deviation of the second group paired, squared, over the sum of the two sample groups minus 2. We're going to take the square root of that. That's going to calculate a pooled standard deviation for us. It sounds complicated, but all you have to do is plug numbers into the formula if you're assuming equal variances. Yes?
It looks like the professor earlier said that she said earlier that she doesn't want us to kind of spend much time in on the whole to concentrate in other stuff that we did, not like putting effort in that whole standard.
Oh, okay, so she says you're going to use line 2, which is unequal variances on SPSS. Okay, but you have to recognize which one's which. But I just also want to go over with you so you know when it comes up in the future, you take another course or you want to you're doing it somewhere else, you're going to have to understand that as well. Okay, so I'm not doing this to punish it anyway. And you need the degrees of freedom because you want to look up the t-score, right? So the degrees of freedom is equal to, now remember, these are the rules for equal variances. Degrees of freedom are equal to n1 plus n2, two sample sizes divided by 2. That's your degrees of freedom. I'm sorry, minus 2. Okay, and then we can calculate our t-score. So now what do you do if they're unequal variances? You just use different formulas, right? In this case, you don't even have to calculate a pooled standard deviation because you're not combining the two of them, using them separately. So the difference in the two means divided by the square root of standard deviation, number 1 over the sample size 1, plus the standard deviation of the group 2 over the sample size 2. Now, there's the formula for calculating the degrees of freedom when you use unequal means is very complicated. So instead of calculating this big nasty thing, most people just take the smaller sample size and use that as the degrees of freedom. Okay, it's conservative. You don't have to worry about it. It makes it easier to deal with. Okay, and what are we missing now? What's the only thing we didn't do here? Right, proportions. Right. So here's the formulas that we would use for calculating the z-score for proportions. Why did I suddenly change from from the t-score to z-score when I went to proportions? What's one of the assumptions that we make with proportions? So we're always going to work with a large sample, right? And that sample, one of those two groups is always going to be greater than 5, but it's always going to be a big sample, right? So since we work on a big sample, we always use z-score instead of the t-score. So the formula here would just simply be, we calculate a pooled standard proportion, right? In this case, we calculate a pooled proportion. And then we calculate, because we're using the proportion, calculate standard deviation. Remember when we're looking at confidence intervals, it was p times 1 minus p over n, and we took the square root of it for an estimate of the standard deviation. So then we would then use this formula for calculating the z-score. We're going to ignore that for now. We're going to come back to it in a little bit. So I'm going to get this out of the way, and we can work on some actual examples. Yes?
So I just want to quickly go back.
Yes.
For the degrees of freedom. What do we need that for? Just to read the table, right?
Degrees of, well, yeah, to read the exactly right, to read the table, to determine, well, in other words, the degrees of freedom represent your sample size, right? It's another way of saying sample size. So the larger the number of degrees of freedom, the smaller your t-value is going to be that you have to exceed, right? Because remember when we looked up in the column degrees of freedom and we went across, the larger the degrees of freedom were, the smaller the critical value of t had to be for us to reject the null hypothesis. The smaller the p-value had to be. When we do this by hand, we calculate a t-value, right? And then we look at the table to determine what the critical value of t has to be. And if our t-score is bigger than the critical value for that sample size, we reject. We know that the p-value is less than 5%. When we use SPSS, SPSS actually calculates a p-value, a probability of being wrong, if we reject the null hypothesis. So when you do it manually, you calculate your t-score. Use the degrees of freedom to figure out what your critical value of t has to be that you have to exceed, and you compare the two of them, right? So you don't really get, if you do it manually, you don't really ever know what the exact p-value is, what the exact probability of being wrong is, but you know it's less than 5%, which is enough for you to reject the null hypothesis. Okay? So when we do this in real life, it'll make more sense. But when we use SPSS, you get an actual p-value because it actually does a calculation and translates it for you. Okay, so what's the procedure we use here? Okay, state the null hypothesis and the alternative hypothesis, right? Specify your significance level. In other words, what's your tolerance for error? So for most of the time, that's your alpha error, right? Alpha or type 1 error. That's usually going to be 0.05 or 5%. You take your sample. You determine you calculate C or T. You determine the p-value. You compare the p-value to alpha to see if your p-value, your probability of being wrong, is less than alpha, and you reject your null hypothesis. Okay? So the p-value represents the probability of being wrong. In another sense, what it means is that's the probability of your getting a result that's that different. The two means are that different, getting that likelihood of getting a difference that big if the two means were really the same for the two populations. You're so far out on a normal distribution that would only occur rarely. So you're only going to be wrong rarely when you say the two means are different. Yes?
So would that mean p-value is the probability of being wrong if we accept the null hypothesis?
Reject the null hypothesis. Okay, if you say that they're different. In other words, if you want the probability that when you say that the two means are different, you reject the null hypothesis, which is usually that the two means are the same. You reject the null hypothesis. The p-value is the probability of your being wrong in rejecting the null hypothesis, right? So you want that to be small. In fact, you want it to be less than 5%. Okay, do it. Yeah. Does this work? Has anybody ever seen anybody actually use this?
Yes.
Oh, good. No, forget it. No, I don't think so. Okay. I don't know, not so much, right? You can see it? Okay, it doesn't look so good from up front. Okay, so now what's going on here? The probability, right? If I have a certain population, and I take a sample of size 100 from this population, these are all the possible results I would get for the mean of that sample of size 100, right? So if I take a second population, and I get, let's say this is 100, right? And this is this has a standard error, standard deviation for a sample means equal to 10, right? Well, this over here 80 would represent about 2.5%, and 120, right? This would represent about 2.5%, right? So if I told you that I took another population, took a sample of 100 people and found that the mean was equal to 90. Well, gee, if I took a sample, it looks like to me, like about 20 or 30% of the time, I would get a sample 90 or less anyway from this population, right? Now, what if I took a sample and it turned out to be 79? Well, I would very rarely get a mean from this population that's equal to 79. In fact, I would get it less than 20% of the time. So that's a small enough frequency of getting a result that's the same as this population for me to say, I'm sure that the two groups are different. I'm going to reject an hypothesis and say they're different. So that's what you're really doing when you look at the p-value, right? That's the area of the curve to the left or to the right of the value that you found, the difference between the two populations. Okay. Now, keep in mind, when I say a two-sided test, right, I'm saying that when I started out, I didn't know if mean one was bigger than mean two or the other way around, or smaller than mean two. So I don't know if my result was going to be to the right of left of here or to the right of here. So anytime I calculate a p-value, I have to, in other words, if I get a z-score is -2, right? Well, that means that that's about 2% here, right? Well, it could have been a z-score of +2, right? Z-score of +2 would be another 2%. So I have to account for the fact that when I started, I didn't know which direction this was going to go. So my real p-value for a two-sided test is 4%, right, or 0.04. And that's what I use as my p-value. If I take a single-sided test, I'm going to allow all of my alpha to be on one side of this distribution. That means my z-score doesn't have to be as big, or my t-score doesn't have to be as big for me to reject the null hypothesis, right? So the single-sided test is less rigorous than a double-sided test. So you almost always use a double-sided test. But it's going to lead to a little bit of confusion as you apply it, because it means that you have to double your p-value after you calculate it manually. So I'm going to close this. I'm going to do some actual examples. Okay, here's our first example. I have 9 numbers there. They're part of the sample. Okay, I'm saying I have a sample size of 9. I'm saying sigma is equal to 9. I'm saying that we know the population standard deviation is equal to 3. Then I'm going to compare it to another population with a known mean of 8. And my alpha, my tolerance for error is 5%. So I have an Excel version of this and an SPSS version of it. Why don't you guys open the SPSS version and actually run this analysis as a single sample test. I'm going to give you about 2 minutes to get it open. And I'm going to open mine here as well, and we'll both run it together.
So single sample test, that's SAV?
I'm sorry. Yes, it's a .sav file.
Single sample?
Yeah. Now, when you do a single sample test, what's it going to do? It's going to find the average, it's going to compare it to something, right? Well, it's got only a single number to compare it to, not a list of numbers like if we had 2 samples. What it's going to do is it's going to look for the difference between the 2 of them. And it's going to say, okay, the mean for the population I sampled appears to be, X bar, appears to be 8. The mean for the sample that I know the population, for the population I know, is 9. So it's going to compare the 2 of them, and it's looking to prove that the difference is something different than 0. It's not equal to 0. So I'm going to go to Analyze. I'm going to go to Compare Means and One Sample T-Test. Okay? There's only one variable there. That's the one that we could sample. I'm going to move it in here. Okay, my test value, what's the value that I'm going to compare it to? What was the mean of the other group?
Of the known?
Yeah, the known group, that mean was, what was it?
8.
Is it 8? Was it 8? Okay.
Yep.
So I'm going to put 8 in here as a test value. So SPSS is going to calculate the mean of our sample and compare it to the mean of the population that we know, which was 8. Okay, and I'm going to say okay. Okay, so SBS now is gonna take this, and it calculated that the mean of the group that we don't know about was equal to 10, right? So we know it's a different mean. The standard deviation of the group that we don't know about is equal to 2.739. Remember I told you that we had two examples there? One of them, we knew sigma was equal to 3. That's known standard deviation. The second one I told you about was we didn't know the standard deviation of, so we had to deduce it from the sample, right? We just deduced it from the sample. We just calculated it came out to be 2.79, and that's what SPSS is going to use in calculating the standard error. How's it going to get standard error? It's going to take that number divided by the square root of the sample size, which is 9. So it's going to be that divided by 3, which is going to be a standard error of about 0.9 or something like that. And then it's going to take the difference between the two means and divide it by that standard error and give us a t-score. And what does a t-score come out to be?
2.19.
Yeah, so does that sound like a big t-score to you? It sounds like a reasonable t-score, right? Right, so if it were a z-score, it's a small sample, so it's hard for us to tell yet if we can reject the null hypothesis. One of the ways we can is we can go to the table and look up for how many degrees of freedom? 8 degrees of freedom. We can look up what the critical value of t would be. Yes?
Is the test value the mean or the sample size?
The test value is the mean that we're comparing it to. SPSS is calculating. We don't know. So before we did this, we didn't know the mean of the sample, right? It calculated it for. We couldn't put the mean in there because we didn't know it yet. So we can only put in there the mean of the population we're comparing it to, which is known. So in this case, SPSS is assuming we don't know the population standard deviation. It's calculating it based on the standard deviation of the sample. Did you see anywhere where I could put in a standard deviation if I knew it? No, I can't. So SPSS will only work with a sample fit standard deviation. Right? If I want to use the population standard deviation, I'm going to have to do it by hand. Okay, so let's see what I got here. So now, my standard deviation, I'm going to run it again so I can scroll up and you can see it. Okay. Okay, so if you can look at it there, you'll see that a two-tailed sigma, the p-value, the probability of being wrong if we reject the null hypothesis, it's a two-tailed test, is equal to what?
0.06.
0.06. Right, so can we reject the null hypothesis?
Failed to reject.
No, on the other hand, we're really close, right? So let's just see the sample size. We would only get this result 6% of the time if the two populations have the same mean. So that's pretty strong evidence that they have different means. Not good enough to reject the null hypothesis. Technically, if our alpha is 2.05, but pretty strong evidence anyway. So this would encourage us to maybe publish anyway, or to maybe increase the sample size. Yes.
You said the p-value is 0.06. Where did you get that?
The sig two-tailed
There's
is what that P is called.
significance. SPSS calls it, sometimes uses different words for the things that we're describing. They call it the significance two-tailed. Okay, so that t-score represents the tail of that normal distribution, a tail of that normal distribution which has a 3% area. So 3% of the time we get a number smaller than that point, and 3% of the time bigger than that point. So this comes out in a manner that we can't reject the null hypothesis. But that's all we need to do. For a single sample t-test, this is what we have to do.
Oh.
Yes.
Oh, I see. I didn't know the sample size was not.
Right.
Okay.
Right? It's
All right,
those
yeah,
9
it's
numbers.
10 minus 1, yeah, that's what I
Yeah,
thought. Okay.
yes.
So the p-value is for a two-tailed and you...
It automatically gives me a two-tailed result, right? Exactly. Now, if this were a single-tailed test, right, I would be able to reject the null hypothesis, right? That in this situation. But most of the time, we're going to deal with a two-tailed test. If we get a chance, I'll just, the main thing that we're interested in is when we set up our null hypothesis, how we set it up so it describes a two-tailed or a one-tailed result. And we'll get a chance to talk about that in a minute. Okay, so let me take a look.
Yeah, Professor, couple things.
I'm sorry, yes, more questions? Yes,
All right, so I was just going to say, from what we learned in lecture, within that confidence interval, 0 is included in it. So therefore,
yeah.
we can fail to reject. So there's lots of
Exactly.
things that
In
we can
other
look
words,
at to
in
fail
this
to
case,
reject.
what it's looking for is, it's looking for the confidence interval, is the confidence interval of the difference
Standard.
between the two means, mu1 minus mu2, right? So what would, if the two populations had the same mean, you would expect the difference to be 0. So you're looking for that confidence interval to either include 0 or not include 0. If it doesn't include 0, you're 95% sure that the two means are different from one another because the difference is greater than or less than 0. Okay.
Why wouldn't you be able to reject the null hypothesis if
I'm sorry,
it was,
fail to reject.
fail to reject if it was a single sample test?
If we're a single sample test, it's less rigorous. In other words, if we ran this as a single sample test, we would instead of 6%, we would wind up with 3% as our p-value. Because we're only looking at one side. We're not worrying about doubling the t-value. Right? In other words, we're only looking at the one end. We're not worried about adding the two ends together. In other words, the result that we didn't assume that we were going to get on the other end.
So how is this not a single test?
One tail.
One tail.
One tail.
Yes.
Okay.
It's two-tailed because we actually doubled. If we looked at this t-value on a table, it would give us a value of 3%. But SPSS automatically doubles that in order to call it 6%, because it's giving us a 3% on the end that it extends on and 3% on the other end. It automatically doubled the p-value. In other words, if this were a z-score instead, it would have said 3%. Yes?
So let's say that we run a one-side test, and
Yes.
we have this, and we conclude that.
Yeah, I'm not even sure SPSS will let you run a
Yeah.
one-sided test. So that's okay, go ahead,
So
yes.
let's assume that we are running
Yeah.
a one-side test, and we have this p-value, and we divide it by 2 to get 0.03.
Yeah, then you
So
can
we
reject the null
will
hypothesis.
conclude that we're rejecting
Yes.
even that we have that confidence interval, like 0 in.
Yeah, but
That
the confidence interval is based on a two-sided test also.
Oh, okay.
It's based on the t-value of the two-sided test.
Professor, I still don't understand how you got the p-value. Can you please explain again?
The t-value, how we got the t-value?
The p-value, P is in Peter.
The p-value
Yeah.
the p-value was calculated by SPSS. We normally calculating would not get the p-value. We would only get a t-score. And then we would have to go to the table to see if that t-score is big enough. Let's do that right now.
Okay, please,
We're gonna open the
thank
same
you.
file. We're gonna open the same file in Excel, and you guys are gonna actually run this analysis. Okay? And we're gonna do it on this one. I'm gonna try to ignore it on the others because it'll take longer. This one will go really quick. Okay, so let's open this file in Excel. Perhaps I made the same mistake I made before. Maybe I should, oh, no, it opened it. Now, okay, here's the exact same file that we were just dealing with, correct? Okay, the data is between A2 and A10. So the first thing I'm going to do is I'm going to calculate the average. Parentheses. Okay, and the average comes out to be 10, which is what we expected. Now I'm going to calculate standard deviation. Okay, same numbers. Okay, the standard deviation is 2.73, just like we got in the same thing SBS got. Okay, so now I'm going to calculate the standard error. And the standard error is going to be equal to the standard deviation, I don't know the population standard deviation, The other problem was going to be 3. We're going to say we knew it, but now we're going to duplicate what SPSS did. Now I'm going to take that, divide it by the square root of the sample size. Sample size is 9, so I'm going to divide it by 3. So there's my standard error. So now I'm going to calculate my t-score. What's my t-score going to be equal to? My t-score is going to be equal to, it's going to be equal to the difference between the two means, which is equal to 10 minus 8. I'm going to put that in parentheses. Divided by the standard error. Okay, I'm going to hit enter. So my t-score is 2.19. So now I know my t-score is 2.19, correct?
Okay, yeah.
Same as we got with SPSS.
Right.
So what's my p-value?
So you
Well,
have,
I can't calculate my p-value. I don't have a z, because I could, for a z-score, I could look it up on the table, right? So what I do with a t-score instead is I go to, remember that number 2.19, okay? I'm going to go to my t-table.
What's the standard deviation for this? Because I did standardize A2, comma, A10, comma, A11, that's the mean, and then what's the standard deviation?
I'm sorry, I'm not
In
sure.
Excel, what
In
is
Excel.
In Excel, STDEV, parentheses.
Okay.
You don't have to use the dot, all these different choices, you can just use STDEV. Okay, so,
Would that be, I see several.
okay, so where is my, okay, under tables, I have my, let's see, T-table, where's the T-table? Okay, so here's my T-table. So for 95% for 8 degrees of freedom, what's my critical value at T? 0.3 is my critical value at T. That means in order to be less than, have less than 5% chance of a p-value less than 0.05, I have to have a t-score that's bigger than 2.3. Right? So indeed, when SPSS calculated it, it came out to be 0.6, right? Which is bigger than 0.05. So now I know I haven't exceeded the critical value of t. So therefore, I can't reject the null hypothesis. Is that okay? You guys okay with that?
So you looked at a t-score of 2.19 on the.
We calculated 2.19,
Okay.
right? This is a table that tells us what the t-score has to be in order for us to reject the null hypothesis. So for a sample size of 9, which is 8 degrees of freedom, the t-score has to be, I guess you can't see my mouse there, right? I thought you could, let me highlight it so you can see. Right, the t-score has to be 2.306.
between
Right?
8 and 9.
That's my critical value of t. My t-score, for that sample size, my t-score has to be that large or larger for me to get a p-value less than 0.05.
But isn't the sample size 9?
But you use n minus 1
Minus
degrees
1.
of freedom.
Okay.
Okay?
Okay.
So now, I'm going to go back here for just one more second. I'm going to go back here for one more second, and I'm going to take one more look at that. And what I'm going to do is, I'm going to take a look at that Excel file that I was just working with. And this time, I'm going to say that my standard deviation was 3 instead of 2.73. Remember I said what happens if you know the standard deviation? So I'm going to hit 3, right? But what happens now? What happens now is my standard error becomes 1, right? And my z-score becomes 2. Why did I say z-score? Because I know what the population standard deviation, I can use z instead. So my z-score becomes 2. Anybody remember what the z-score has to be for you to reject the null hypothesis at 5%? 1.96. And it's bigger than 1.96. I could actually look this up on the z-table and it'll come out to be -2 if I look that up on the z-table. SCT. There's a z-table. I'm going to use -2 instead of positive 2. It's going to be a little easier to look it up. Here's -2.0. So that represents an area on the no, left side of normal distribution of 2.3%, roughly 2.3%. 2.3%, remember I got to account for the other tail, I have to double that, it comes out to 4.6%. So a two-sided test is still less than 5%. So knowing the population standard deviation, let's use the Z-score, which made it more likely for you to reject the null hypothesis. So we did this, we did the same problem, single sample t-test, 3 ways. We used SPSS to do a t-test. We did a t-test using Excel. And we did a Z-test, a Z-score test, because we assumed we knew the population standard deviation using Excel as well. We couldn't use SPSS for it, because it'll only do the calculation of the sample you actually produce. Okay? Let's move on to the next one. Let's move on to the situations where we have 2 samples. That's more common. We take group A, group B takes samples from each. Okay, let's see. And I gotta go back a little. Okay, as you go into, let's see, 2 sample t-tests. Open the first one I want to open is the one that says SPSS and one says equal variances. Test equal variance. Okay, so here's a test that involves gender, right? Males and females. If you look at the variable view, you'll see that 1 represents male, 2 represents female, and there's different scores. Maybe the test scores, who knows? Right? Doesn't really matter. So I am going to compare the means for males and females. Notice how it organizes it differently than SPSS. The gender is in one column, right? That's a variable. The actual score, we're taking the average of, the numerical variable, is in a different column. In Excel, very frequently you would put males and females in one column, females in another column. SPSS strictly sticks to this format of separating the variables by columns, right? So the actual format looks a little bit different. So I actually can turn on the variable labels, so you can see which is males and which is females. Whoops. Yeah, it's hard to, it's very awkward here working with your hand yourself into the slot. We're working through a male slot. So anyway, now I want to do this analysis. So what am I going to do? I'm going to go to Analyze again. Yes? I'm sorry.
Coding, like the previous view.
Yeah.
Where do we go again?
Go to the variable view. Oh, you want to turn that on and off? Well, first in the variable view is where you define that. So for gender, I define the values for gender as 1 for male and 2 for female. Once you've done that in the data view, SPSS knows now that you defined 1 as male and 2 as female. And you can turn that on and off in the view by toggling the view labels. Right? Just turn that on and off. Just click it, turns it on, turns it off. Okay? So now I'm going to go to Analyze. I'm going to go to Compare Means. That's exactly what we're doing. Except this time they're independent samples t-tests. Right? The 2 groups are independent samples. I'm going to click on that. And I'm going to move into the test variable, the score, okay, because that's my numerical variable. That's the one I'm going to find the average of, average for males, average for females, and into the grouping variable, I'm going to move gender. In other words, that's how the data is grouped. It's grouped by males and females. Those are the 2 separations for that variable. Now notice it has a little box down here that says define groups. I'm going to click on that.
If the values are to be different, is it because one's numerical goes into test variable and the other one's categorical?
Right, the numerical variable is just the actual number. Like it could have been blood pressure. Right? So you don't have to code that. You don't have to. You just tell SPSS what that number is. The grouping variable, the other categorical variable, if we're putting in 1 for female and 2 for male, now you have to tell SPSS what that is so that when it produces a table, it makes some sense. It'll still work, but you won't be able to tell someone that's reading that table wouldn't be able to tell which is male and which is female. Okay, so I'm going to go in here. Now notice define groups. It's asking you to tell them what the values are. There were only two values, 1 and 2. So I'm going to put in a 1 and 2 there. Now you would think a program that, the full price of this program is like $1,000, you would think that it would be able to do this on its own, figure that out. Why is the reason why you have to tell it what the numbers are? Anybody take a guess?
The labeling,
What's that?
the labeling on the output table?
Well, yeah, well, you put the labeling on, you told her what 1 and 2 was already. The reason for that is, let's say instead of gender, which only has 2 values, you used ethnicity. And you said 1 for African American, 2 for Caucasian, 3 for Hispanic, 4 for Asian Pacific Islander, and so on. You'd have more values than 2. So in that point, you could tell it which 2 groups. Remember, t-tests can only compare 2 groups at a time. You could tell it, oh, compare group 1 to group 7, or group 2 to group 4. That's why it wants to know that. And that's why it asks you to put that in there, even though we know there's only 2 groups.
Okay, so you're defining the values.
Exactly,
One,
but
two,
you define it in
1,
2
2, 3,
groups.
4, but then that's just one group, and then the
Right.
next group could be 4, 5, 6.
Yep. Okay, so now here's our output, right? And this is, whoops, oh no, it's in, I could do it right there, I guess, I could. Okay, so here's our output. So let's take a look at this. Okay, so what do we have here? First of all, we have 2 lines. What do the 2 lines tell you? It tells you equal variance is assumed, or equal variance is not assumed. Professor White had just told you to use which one?
Not
Not assumed, right? Because she's taking that as the more conservative approach. Okay, I'm just gonna, just so you know for the future, I'm gonna show you how you would often use this table. Okay, so look at this box over here. You're not, if you're gonna just take that bottom line all the time, this 4x4 box here, Levine's test for equality of variances, you're gonna ignore that, just use the bottom line. However, in the future, when it comes up, you're going to look at this and you're going to say, you know, this is testing for the equality of variances. And there's 2 possible outcomes here. One is the variances are equal, right? The other is that they're not equal. Now, based on what you've learned so far about null hypothesis, alternative hypothesis, what's going to be your assumption to start off with? That they're equal, right? And you're going to hold that assumption until this test proves it differently, right? So this test is its own little t-test kind of. Right? And it's going to evaluate the variances, and it's going to say, well, gee, let's start here. If the p-value is less than 0.05, I'll reject this null hypothesis, and I'll use the lower line, right? In this case, it's telling you it's okay to use you fail to reject it because the significance of the p-value is so big, much bigger than 0.05. So it's telling you you can use the upper line here if you want. I did this on purpose because if you look, what's the standard deviation for males? 2.5. What is it for females? They're very close, right? So that's why this particular test came out in a way that it told you you could use the upper line. Right? I'm going to show you the data in another format in a second. Okay, so we're going to use the lower line. If you use the lower line, the t-value is 1.86. So far, it sounds like you're going to be able to reject the null hypothesis? No. Almost certainly not, right? It's not even a good number for the z-score, right? That's your t-value. In fact, look, in this case, they're so close, it really doesn't matter. Your degrees of, remember that really funky formula for degrees of freedom? I told you just use the smaller sample size. That's why the degrees of freedom on the lower line are such a weird number instead of just sample size -2 or something like that, right? So that's the degrees of freedom. This is the significance. This is the probability of being wrong if you reject the null hypothesis, that the 2 means are different, that the 2 means are the same. And what is the significance? It's 0.085, so you fail to reject the null hypothesis. If you do reject the null hypothesis, you have an 8.5% chance of being wrong. Okay, if I go across here, remember that this is the confidence interval of the difference. Our assumption, no hypothesis, the difference is 0 between those 2 means. And again, -3, -0.3, +0.4, 0 is between those. That's a further confirmation that we haven't proved that they're different. Now you notice the 2 lines are pretty much the same. I'm going to do the same exercise on the other file that says unequal variances. Okay. So hopefully you guys do this with me, right?
Yeah.
Okay, so minimize this. And I'll get this out of the way for a second. Find equal variance, two sample and equal variance. Okay, again, same kind of file. I'm going to go to analyze, compare means, independent sample t-test. I'm going to move score into the test variables. I'm going to move gender into the grouping variables and code it. Define the groups, 1 and 2. Okay, I'm going to say continue, and I'm going to say okay, and see what my output looks like this time. Okay, how's that change my output? Okay, let's take a look at this. Take a look at the standard deviations now. The first one, I changed the female numbers, because you probably noticed that's going on. The means are the same, right? The two means are the same. The standard deviation for males is 2.5, for females is 1.1. One is almost double what the other is. They're very different. Well, let's see how the means test for qualities, quality variance will work out. Equal variance is assumed. The p-value is less than 0.05. So that means I should reject this null hypothesis and use the bottom line. Again, on an exam, since Professor White and I are going to be grading it, for simplicity's sake, you're going to use the bottom line anyway. But in this case, this test tells you should use the bottom line for this analysis. Yes?
So I can kind of see why you're doing this now.
What's that?
I can kind of see why you're doing this pooled t-test now.
Yes.
Right? It's just kind of another way of helping us support that we could reject the null hypothesis.
Exactly. In other words, pooling it gives you an advantage, because
Gives you
then you have
another-
a better handle on standard, if you're allowed to do it.
Gotcha.
But these two standard deviations are so different here, you can't justify doing it. So we're going to go across here on the t-test. What happened this time? Well, the standard deviations are different this time. This time we got a t-score of 2.2. Only remember they're different numbers now, right? 2.2. The significance, two-tailed is 0.04. This time I can reject it on hypothesis. Why is that? Because the t-score is so much bigger than it was before. Okay, so that t-score, and that t-score goes along with this degrees of freedom. If you look up like 12 or 13 degrees of freedom on that table, the critical value of t is probably something like 2.2, and this number is bigger than 2.2, so the significance is going to wind up coming less than 0.05. So that's our two ways that we might be working with two sample t-tests. Sometimes could be equal variances, sometimes could be unequal variances. As far as we're concerned, when we use SPSS, we're always going to assume unequal variances. Equal variance is not assumed.
But why would you reject? No, you are rejecting.
Yeah.
The null hypothesis.
Yeah.
Okay.
And then if we look over, 0 is not included again.
Yeah, you look over here. No, 0 is not included this time, right?
Right.
0.59, but these are all plus numbers, so 0 is outside of that confidence interval. There's no difference, 0 difference.
And also, question.
Yes.
For the BIOS test, we have 0.03, which is less than 0.005. So that also supports the fact that we are rejecting the null hypothesis.
Oh, you mean up here? This one?
No,
Levine's
Oh,
significant.
yeah, that
This
would
supports the idea.
tell you that you can reject the null hypothesis that the variances are equal, and you should use this one instead. You can't justify using the top line. The top line would be better for you to use. Look, the significance is lower, the p-value is smaller. The top line gives you an advantage, it's better, right? But we're saying we're going to like give up that advantage to simplify things and use the bottom line all the time. We would have preferred to use the top line here because we would have had a better chance of rejecting the null hypothesis. We got lucky in both of them rejecting the null hypothesis, but we're going to go with that, which is still less than 0.05. The last thing I just wanted to talk about, I tried to go a little slow, and on the feedback that we got, one of the things that we had an issue with was I was going too fast quite a bit. I tried to slow down a little bit. It's really tough to get all this stuff in. with questions and stuff like that.
I wish we did that.
You know what, maybe what we'll do is another Saturday again, we'll have like an online session. It occurs to me, I didn't, I uploaded it to YouTube, I didn't give you the link. I'll post the link. I'll post the link for the last one.
Thank you.
Okay, wait, 1 second, don't go away yet, I just want to show you one more thing. Okay, and the last thing that we had in terms of files was the proportions. I'm sorry, I'm going to show you prepared samples, and then you can run out. And I'll do proportions on Sunday. Prepared samples, these are the same patient that took the placebo for a week, got measured, took the drug for a week, and so on and so forth. They didn't necessarily take them in that order. They might have taken the placebo 1 week, the drug another week. This is paired samples. What we're going to do here, for instance, if you're looking at weight gain, for instance, weight loss, right? Well, if a person started at 300 pounds and they lost 20 pounds, that might be more significant than a person starting 150 and losing 7 pounds. So you can take advantage of the fact that you know where the person started and look at the difference from where they finished. So we get a big advantage there. So how does this work? What's going to happen is SPSS is going to find the difference between the placebo and drug for everybody. This is 0. This is +2. This is +4. This is -3. It's going to take those and do a single sample t-test analysis on it and compare it to what number?
Yeah.
0 difference. And it's going to do that t-test and tell you whether there's a 0 difference, between. But the paired sample t-test is really the same as a single sample test. Yes?
So when you say for just against 0, that means the number for testing will be 0 in this.
Exactly right. And SPSS actually will do that automatically.
Okay. Unless otherwise specified.
Yeah, I'll do both of these. We can go back over this.